Bias. What is bias? Bias is an error from erroneous assumptions in the learning algorithm. Bias occurs when an algorithm has limited flexibility to learn the true relationship from the dataset. An algorithm that has high bias would likely make wrong predictions. Bias is the algorithm's tendency to consistently learn the wrong thing by not taking into account or consideration all the information in the data, or it's also called underfitting. Parametric algorithms, algorithms that summarize data with a set of parameters of fixed size independent of the number of training examples, are prone to high biases. Examples of parametric algorithms are linear regression and logistic regression. Variance. What is variance? Variance is an error from the sensitivity of the model to a small fluctuation and changes in the training dataset. High variance can make an algorithm susceptible to noises in the training data, meaning the algorithm is likely to fall in the trap of local variations so that it would actually miss the global trend that we are interested in. Variance is the difference between the many predictions one algorithm makes. That's why it's called variance. It comes from variation. Variance is the algorithm's tendency to learn random things, irrespective of the global trend or relationship that we are looking for. A high variance tends to occur when we use complicated models that can be too much influenced by the training data. This is also called overfitting. Bias versus variance. To learn more about these two concepts and learn about their differences, let's juxtapose these two concepts. Bias is the difference between the average prediction of a model and the correct value of the target variable. A model with high bias would pay little attention to the training dataset and oversimplifies, which is also called underfitting. A high bias model would have high error on both the training dataset and test dataset. So if you have a model that has poor performance on both the training dataset and test dataset, it is suffering from underfitting or has high biases. On the other hand, variance is the variability of your model's prediction for a given data point based on the different training data that you used. A model with high variance pays too much attention to the training data, but has poor performance on test dataset. So if your model has a good performance on your training dataset, but a bad performance on the test set, then your model is probably suffering from the overfitting or high variance. Also, a high variance model, because it's too adjusted and too attached to the training dataset, would have different performances each time that you change the training dataset. The mathematical context of bias and variance. So what is the mathematical relationship or definition of these two concepts, if they have any? Assume there is a relationship between a target variable y and independent variable x. Y is equal to f of x plus e. F is the relationship and e is the error term. We assume it is normally distributed with an average of 0. Now, for a data point x and y, we make the prediction y hat. If you remember from a statistic, this is called y hat. y hat, our prediction, is f prime of x. This is our prediction. We can't really accurately find the relationship f, so instead I use f prime, which is close to f but not really. The expected squared error of our prediction error is the expected value of the difference between the actual value target variable minus our prediction squared. If we actually decompose this relationship, it's going to be like this. The first term is the expected value of the relationship that we predicted minus the actual relationship squared, plus the second term is the expected value of the difference between the relationship that we predicted minus the expected value of the relationship that we predicted squared, plus the variance of error or sigma squared of error. The first term here is bias squared. So if you take a square root of this, it's going to give you the bias. The second term is the variance. And the third term is called irreducible error. Irreducible error is the error that cannot be reduced. That's why it's called irreducible. No matter how good of a model you use, it cannot be reduced. It's a measure of amount of noise that you have in your data. Complex models versus simple models. Let's see the differences between the behavior of a sample complex model and a simple model on a training dataset. Suppose this is our data and the relationship between them. The feature variables are shown on the x-axis, so this is our x variable, and the target variable, the y, is shown in the y-axis. The little circle are actually our data points, and this line right here that I'm going to follow it shows the true relationship in our data that we want to uncover. As you see here, there is noises in our data because there is a difference between the true relationship and there is these differences, this variation, meaning that the relationship doesn't accurately cut through every data points or predict or cover every variations in our data because there is noise or irreducible error in our data. However, the general trend that is shown here by the blue color is pretty clear. So we want to use a complex model and a simple model to find this relationship. The first thing that we need to do is to split our data into training set and test set so that we can train our algorithms using the training data set and then evaluate their performances and on the test data set. So we randomly split our data into training and testing data set. Here, the training set is shown by the blue color and the test set is shown by the green color. All right, let's see how would a complex model fit into our training data and find the relationship. A machine learning model, a complex model with lots of flexibility, having many parameters to control its behavior and adapt to differences and changes and variations in the data, may actually have very little bias, as you see in this picture. So a complex model, as you see here, would cut through every up and downs, and it discovers every changes, every little variation in our data. So as you see here in this specific picture, our model, our complex model has a perfect accuracy. The problem, however, is it may actually be too much focus on the training data sets by attaching to a lot of or shaping into a lot of variations and data in the data points that we have, so that it may actually lose focus of the overall relationship that we want to uncover. This trend is called overfitting. All right, let's now figure out how would a simple model go through this process. A simple model doesn't have a lot of parameters to adjust to the variations and the changes in the data set. So it may be incapable of capturing the true relationship. So the true relationship, as you see here, it's shown by this blue, not very perfect. But the relationship, the predicted relationship, which is shown by red color here, does not really match that or capture that relationship shown by blue, right? So because the simple model doesn't have that flexibility of a complex model, it doesn't have a lot of parameters to adjust to changes or predict changes into in our data. That's why it's underperformed even on the training data. It cannot uncover the true relationship. This is called actually bias, high bias. The model has high bias, or a simple model has high bias, or it's actually underfit. Let's learn more about bias and variance using our examples of a simple algorithm and a complex algorithm. Although the simple model that we had, a linear regression, has high biases, as you noticed, and low accuracy rate for the training set, it can actually make more accurate predictions for the test data set than our more complex model with low bias but high variance. Here we say that the more complex model is actually overfit. So let's take a look at the picture that we had before, the performance of a simple model and our more complex model. So the training set is shown by the blue line here, which was used to train the simple algorithm and the complex algorithm. And the test data set is shown by green circles here. So as you notice here, although our simple algorithm has biases, there is differences here. Unlike our complex algorithm, which cuts through every little variation, data points, it has perfect accuracy for the training data set. But if you look at our if you look at our simple algorithm, it doesn't actually miss the true relationship or the general trend, which I'm going to show it by this line here. Also for the complex model. So unlike the simple model, the complex model actually, as you see here, kind of misses the overall relationship, especially if you look at the test data points for the simple algorithm. It doesn't have a great performance for the training data set, but that same performance is also applied for the test data set. So the bias, the variation for the performance for both data points, the test data set and the training data set, is the same. Unlike the complex model has zero biases. It is perfect accuracy for the training data set, but it kind of misses on, it gets a lot of biases and has a lot of errors for the test data set. And also it kind of misses on the overall trend here shown by the blue color. Because of this, the more complex model may actually sometimes perform well and some other times perform poorly, meaning its performance is not consistent. The more complex model is not actually a stable algorithm. However, the simple model with low variability usually produces good or average predictions consistently. So it's a stable algorithm. A good model has low bias and low variance. Low bias and low variance. Example of a good model. So a simple model would underperform and a complex model would overperform. So what should we do? Let's get back to our example of a simple model. A simple model like a linear regression that generally has no parameter to control the complexity might not be able to catch and find any pattern or relationship and would possibly underperform even on the training dataset, which this problem is called underfitting. So similar to the previous problem that we had, in this problem also we see a linear regression that tries to find the relationship between in our data by a line. And as you see here, we have high biases between our prediction, the line, and the real data that are shown by little circles here. So our model suffers from underfitting problem and it has high biases. On the other hand, if we make a complex model that has a lot of parameters that would possibly be influenced too much by the local patterns and changes and up and downs, and may miss the general and overall pattern in the data, and would likely overfit, meaning too much attachment on the training dataset. As you see here in this example, the model is overfit, is too attached and too much influenced by the training dataset, such that it might actually have missed the overall and general relationship. A good model is actually something between these two, not too simple and not too complex. A good model that is able to identify the general pattern and relationship and also is not influenced too much by the local up and downs and variations in the training data set. So it would be something like this. This is our ideal good model that doesn't have high biases, it has low biases, it also has low variations and variance. But it's actually easy to explain a good model, but very difficult to make. How to pick a model? Generally, simple models are easy to develop and easy to implement, but their performance on both the training dataset and test dataset might be unsatisfactory. So we would say we would have underfitting problem. Our model has underfitting problem or high bias. On the other hand, complex models are generally more difficult to build and would require more time and possibly more data. However, they would provide better performance, especially on the training dataset. But oftentimes, the performance of complex model on training data might be too optimistic, meaning they would not yield the same level of accuracy on test dataset and potentially on new dataset. This is called overfitting problem. But where should we set the bar between too simple and too complex? Let's take a look at this graph on the right. On the x-axis, we have the model complexity level, and the y-axis, we have the accuracy level. If your model is too simple, it doesn't have a lot of parameters, it would have high bias problem. It would underperform on both your training dataset and test dataset. If your model is too complex, on the other hand, it might actually have very accurate level of on your training dataset, but it's going to disappoint you with its low performance on the test dataset. So as we move through the complexity of model, making the model more complex, the accuracy of the model on the training dataset is going to increase, but there is a point where the accuracy of the model on the test dataset is going to underperform. So we need to find this best model balance right here, which has high accuracy, the highest accuracy for the test data and also for training data. However, this is not easy to find. The bias variance trade-off. Suppose you have a simple model. It is likely that it has high bias because it doesn't have too many parameters to control its behavior. For example, suppose your model concludes that every person named Adam is a nice person. This presents a high bias and low variance problem. You might want to fix the problem with your model, with its high bias problem. So you may want to make your model more complex, but that could result in high variance problem. Your model could, for example, conclude that Adam is a nice person one time and a terrible person other times. Unfortunately, you cannot minimize bias and variance both altogether. So you would need to find a balance between these two. Bias, variance, overfitting, and underfitting. What's the relationship between all of this? Let's see. A model that has low bias but high variance has overfitting problem. The model would make different prediction each time you change the training dataset. On the other hand, a model that has high bias and low variance would make similar predictions like one another, but on average, they are all wrong. To make this more clear, let's take a look at this graph right here. This graph has two axes. The y-axis shows the bias from bottom to top, the bias increases. On the x-axis, we have the variance. From left to right, the variance increases. At the low bottom here, for the low bias and low variations, this is the ideal place for us. The model hit the target consistently. It has learned the right thing, and with low variation, consistently have a good performance with a good accuracy, high accuracy. Here, we have a model that has low variation, but with high bias. It means that the model has learned the wrong thing, and it consistently hit the wrong target. So here we say the model has underfitting problem. On the bottom here on the right, we have a model that has high variation but low bias. It has learned the right thing, but sometimes it hit the target, sometimes it not. Its accuracy varies each time you change the training data set. So we say that this model have overfitting problem. On the top right, we have a model that has high variance and high bias. This model is too complex and sometimes hit the target and sometimes not, and it has high variation. However, most of the time it does not hit the target. Between these two models, a model with high variation and high bias and a model with low variation and high bias, which one do you think is worst? I'd say this one is worst because at least this one hits the targets sometime, but this one with low actually variation hit the wrong target consistently. All right, let's now break down the errors that we have for a model into variation and bias in a different way. So in this graph, you see the algorithm complexity on the x-axis. The algorithm complexity increases from left to right. And we have the error on the y-axis. The error increases from bottom to top. The error is shown, the total error is shown by the red pinkish color here. When you increase the complexity of the model, the error decreases. Also, the bias decreases. However, the variations or the variance in the model would increase. A too complex model had low bias. It can pretty much accurately fit to the learning training dataset. But each time that you change your training dataset, it's going to get a different prediction. So it has high variations. So as you see here, there is a balance here when these two actually crossover. So this point is our ideal model, optimal model. Avoiding overfitting. Understanding, detecting, and avoiding overfitting is one of the most important skills in applying supervised machine learning algorithm that we all should master. There are some methods to find the right balance for model complexity and accuracy. Regularization, boosting, and bagging are among those methods that we are going to learn in the following lectures.